Good morning, guys. Nice to meet you here. Just want to say that because I have to teach three different subjects on Monday and Thursday, so it's quite tough for me. Also, for me, after teaching econometrics, my brain actually doesn't work well. So, in order to reduce the teaching load, and also for you guys, I decided to make a recording for you. So this recording gonna be about the introduction about chapter 2, which is multiple regression analysis. But I promise I won't do it for a very long time. We also have the class on Thursday, okay? But maybe it's not that intensive, okay? Maybe more we can discuss about the thing that you don't understand from the introduction. So please allow me to do this. And also, I think you can review this recording whenever you want or you don't understand, right? I hope it's helpful. So let's get started. Last time we learned simple regression, right? 1y, 1x. For example, study hours, explain exam score. But think about it. Is study hours the only thing that affects exam score? What about IQ, class attendance, sleep? In real life, one outcome always has many causes, right? That means one Y always has many X to explain. That's exactly the problem with simple regression. If we leave out other important factors, our estimate of the effect we care about can be wrong, which means biased. So today we move to multiple regression. 1y but many x, okay? This lets us study the effect of one variable while holding others fixed. This holding others fixed idea is the heart of empirical economics. It's how we try to isolate cause and effect from messy real-world data. That's what chapter 2 is about, how to estimate this model and what conditions we need for our estimates to be trustworthy. Okay, so let me write it down. 1y but many x. Okay, this is the idea. The book's definition, this model explains variable y in terms of variables x1, x2, all the way through to xk. So in plain words, instead of one suspect, now we have many suspects trying to explain y. Look at the equation here. Y equal beta 0 plus beta 1 x1 plus beta 2 x2 plus all the way through to beta k xk and mu. Same as before, beta 0 is the intercept, okay? It's the y's starting point when everything else is 0. And for beta 1, beta 2, all the way through to beta k, those are slope parameters. Each one answers, if this x goes up by 1 unit, how much does y change? Okay, holding all other x fixed. That phrase, holding other fixed, is the whole point of multiple regression, we have mu, the error term. It captures everything affecting y that we didn't or couldn't include in our model. Okay, error term, disturbance, unobservables. Okay, I hope right now you know it, okay, about the error term mu. Let's think about one example. Suppose y is wage. X1 is education. X2, maybe we can have experience. So actually, beta 1 tells us the effect of one more year of education on wage for people with the same experience level, okay? That's something simple regression couldn't never isolate on its own. So why do we ever bother with multiple regression? There are three reasons. First, we can include more explanatory factors, okay, like more suspects that explain why. Second, and this is the key one, we can explicitly hold fixed factors that used to be hiding inside mu. In simple regression, experience was stuck in the error term. Remember, in simple regression, we only have wage and education, right? So experience was stuck in the error term, silently messing up our estimate of education effect. Now we pull it out and control for it directly. Third, it lets us build more flexible functional forms. We'll see this later with things like quadratic terms or interactions. Now let's look at the wage example, okay? So here we have wage equal beta 0 plus beta 1 education plus beta 2 experience plus mu. Notice the difference from simple regression. Beta 1 now measures the effect of education explicitly holding experience fixed. Okay, here is the experience. Compare two people with the same year of experience, okay, same year of experience, one more year of education raises wage by beta 1. That's much cleaner, more believable estimate than before because experience is no longer contaminating mu. But here is the question. Here we have 2x, right? Education and experience. So the question is, how many regressors are enough? Think about it. Okay, how many x are enough? The answer is there's no magic number, but there are clear principles to guide you, okay? The question and the answer. There's no magic number, okay? There's no definition that how many you should get. But you need to follow the principle. So what is the principle? You should include variables that belong. What does it mean, belong, right? What does it mean? Okay, it means if a variable xj belongs in your model, if both of these are true, the first one, it affects y, which means it's economically relevant. Second, it's correlated with one or more of your other regressors. What is regressors here? Regressors means other x, right? Okay, so this is the principle, okay? It affects y and it's correlated with one or more of your regressors. If you leave out such a variable, you got omitted variable bias. That means your estimates of the other coefficients will be wrong in a systematic way, okay? You saw it from your assignment, right? I asked you about your understanding of multicollinearity and omitted variable bias. Okay, let me give you one example. Suppose you are regressing wages on education. Okay, let's use this one. You are regressing wages on education. If you leave out ability, and ability is correlated with education, your education coefficient will be biased upward. It's picking up the effect of ability too. Okay, so there are two mistakes you can make. Okay, there are two mistakes. What are they? And what it's called, okay, how we call it in econometrics. And what is the consequence of that mistake? Okay, the first one is like you have too few variables. This means that it might be underfitted. Or we call this, because you have too few, right? Too few, so you might have omitted variable bias. The consequence is that our estimate will be biased and inconsistent. The other way around is like you have too many variables. In this case, we call it overfitting. Because there are some irrelevant variables. So the consequence is that you might have a larger standard error. But estimates stay unbiased. Okay, let me enlarge it. Okay, so take a look at those two mistakes. The first one, too many. The first one, too few. You're gonna have biased and inconsistent estimates. Second, too many. You're gonna have larger standard errors, but estimates stay unbiased. Notice the asymmetry. Omitting relevant variables is worse than including irrelevant ones. Including an irrelevant variables just costs your efficiency because you're going to have a wider confidence intervals. But omitting a relevant one corrupts your estimate entirely, okay? So this one is worse, omitted variable bias. And here, let me help you with the practical rule of thumb. How many X, what kind of X should you incorporate in your model? The first rule, it starts with theory. This means what does economics tell you drives why? Those variables go in first. The second one, think about what's correlated with your X of interest. Okay, this means anything correlated with both Y and your key regressors must be controlled for. The third one, watch your sample size. A rough guide is you want at least 10 or 20 observations per regressor. Suppose if you have your observation with n equal 100, don't throw in 30 variables, okay? Next one, avoid the kitchen sink approach. What does it mean? So adding every variable you can think of inflates standard errors and can introduce multi-collinearity. Okay, when regressors are highly correlated with each other, it becomes harder to isolate individual effects. Okay, so let me repeat it again. Suppose you are adding every variable you can think of inflates standard errors, okay? Because more variable, you're gonna have a higher standard errors, of course, higher variance, and can introduce multi-collinearity. This means that multi-collinearity means when regressors are highly correlated with each other. It becomes hard to isolate individual effects. Next one, check R square carefully. R squares always increases when you add variables. So you can use adjusted R squares instead. Okay, so it because adjusted R squared penalized you for adding variables that don't help. So you can see we have the bias and the variance trade-off. Think of it like a zoom lens. If you have too few variables, your lens is pointed in the wrong direction. Okay, we call this bias. But if you have too many variables, your length is shaky, okay, which means higher variance and also imprecision. And you want the lens steady and pointed right. Here is the real example of why we need to control for other factors. Here we have the model, average score, equal beta 0 plus beta 1, expenditure plus beta 2 average, family income plus mu. Okay, so think about it. School's average test score expanded by per student spending and average family income. Now, why do we need average income in the model at all? Because richer families, schools tend to spend more per student, right? School financing often comes from local property taxes, so wealthier areas fund their schools better. So expenditure and average income, they are correlated. So here is the problem. If we run simple regression with only expenditure and leave average income out, average income doesn't disappear. It goes into mu. But since average income is correlated with expenditure, our estimate of beta 1 gets contaminated. It won't just capture the effect of spending. It will also pick up part of the effect of family income riding along with it. So without average score controlling for average income, we would think spending has a bigger effect than it really does. Some of that effect is really just richer kids doing better for reasons unrelated to school spending. This is the core motivation for multiple regression. Control for co-founders or your estimate is biased. Okay, let me write it down. The core motivation of multiple regression. Okay, control for co-founders or your estimates is biased. Okay, so I showed you here, per student spending is likely to be correlated with average family income at a given high school because of school financing. Omitting average family income in regression would lead to biased estimate of the effect of spending on average test scores. In a simple regression model, 1y, 1x, effect of per student spending would partly include the effect of family income on test scores. This example shows that third reason for multiple regression, flexible functional forms. Okay, so here we have the model. Family consumption equal beta 0 plus beta 1 family income plus beta 2 family income squared plus mu. Notice something different here, right? What is it? We have both x are the same variable incomes, right? Family incomes, but here is income and income squared. This isn't about controlling for a co-founder anymore. It's about letting the relationship between income and consumption bend. What does it mean, bend? Why would we want that? Because in real life, an extra 1,000 baht probably doesn't increase consumption the same way for a low income family as for a high income family. Okay, the effect isn't constant, it changes depending on how much income someone already has. A straight line can't capture that. Okay, so we need a curve line, a curved line can. This is what I mentioned to you yesterday, right? So think about the asymmetric effect, okay? We have low income family and also high income family. Of course, extra 1,000 baht, the effect of extra 1,000 baht is different for those low income and high income, okay? So we need to consider the squared term. Now, here is the tricky part, interpretation. Okay, how can we interpret? You can't just look at beta 1 alone and see that the effect of income. Look at the formula here. Delta consumption over delta income right now is approximately equal beta 1 plus 2 beta 2 income. Actually, this is about differentiate, right? So you get the parameters, okay? Let me show you beta 1, and 2 beta 2. This is how you take differentiate. So what does it mean? This tells us the effect of one more unit of income depends on the current income level, depends on how much income is already there. So the marginal effect isn't one fixed number anymore. It changes as income changes, okay? This is the price of flexibility that I mentioned here, flexibility. Coefficients alone doesn't tell the story anymore. You need to plug in a specific income level, okay, to get the actual marginal effect at that point. But here, this model is still a multiple linear regression because it's linear in parameters. Okay, be careful. Beta 1 and beta 2, they are linear. Okay, we said linear in parameters, okay, parameters. But it captures a nonlinear relationship between income and consumption. So right now, the effect of income on consumption depends on your current level of income. Okay, so the golden rule for quadratic model, because here is the quadratic term, never, okay, never interpret beta 1 or beta 2 alone. Always compute the marginal effect, like beta 1 plus 2, beta 2 times income at a meaningful value of income, okay? So suppose the mean or a low versus high income level. Let me repeat it again. Never interpret beta 1 or beta 2 alone. Always compute the marginal effect beta 1 plus 2 beta 2 times income at a meaningful value of income. Okay. This example combines everything we just saw. Okay, we learned log terms and quadratic terms in one model. Okay, so here we have log salary equal beta 0 plus beta 1 log sales plus beta 2 CEO tenure plus beta 3 CEO tenures squared plus mu. Let's look at the first part, which is the log salary on log sale. When both y and x are in logs, okay, beta 1 has a special meaning. It's an elasticity and constant elasticity. It directly tells us if sales goes up by 1%, salary goes up by beta 1%. This constant elasticity form is extremely common in economics, as I mentioned to you yesterday, because it gives us percentage effects. directly. Second part, CEO tenure and CEO tenure squared. Same idea as the income example. CEO salary doesn't rise at a constant rate with tenure. The effect of one more year probably change depending on how long the CEO has already been there. Makes sense, right? Depending on how long the CEO has already been there. So again, quadratic form gives us flexibility. Okay, quadratic terms give us flexibility. Now, the big takeaway at the bottom. Linear regression doesn't mean the variables are linear. Look at this model. We have logs, squares, all sorts of nonlinear looking terms in X. That's totally fine. What linear really means linear in parameters, okay? Not in the variables. Linear in parameters means beta 1 and beta 2, beta 3. Each beta multiplies its term and they simply add up. We don't have beta squared, okay? We don't have beta 1 inside a log. We don't have beta 1 over beta 2. As long as the betas enter this sample additive way, we call it linear model. No matter how twisted the axes themselves are, this is a very important distinction. It's the actual technique definition of linear regression. And it's why we can transform variables so freely without leaving the linear regression framework. Okay, remember, linear regression means linear in parameters. So parameters here we have beta 1, beta 2, and beta 3, right? Linear in parameters. Now, let's move from the model to actual estimating it, okay? We see our old friends, OLS again. Same OLS idea as simple regression, just extended to many X, right? So we need random sample. We observe n individuals, and for each one, we have all the X and Y. Nothing new here, just more columns of data per person now, not just one X, okay? Random sample, and we have the regression residual, which is mu I hat equal y I hat minus beta 0 hat minus beta 1 hat xi1 minus beta 2 hat xi2 minus all the way through to beta k hat xik. Remember, the residual equals the actual y minus the fitted y hat, okay? So the same concept as before, we are just subtracting off more terms now, one for each x. So the OLS job is that we choose beta 0 hat, beta 1 hat, beta 2 hat, all the way through to beta k hat to minimize the sum of squared residuals, okay? Let me write it down. Minimize the sum of squared residuals. which is our symbol here, summation of mu I hat squared, okay? This is the idea of OLS. In words, we want to find those coefficients that make our prediction error squared and added up as small as possible. The intuition doesn't change from simple regression at all, right? OLS finds the best fitting line, except now it's a best fitting plane. Okay, right now it's not a line. It's not a line. Built for simple regression model. Okay, simple linear regression. Because we have one x, one y, so it's a line. But here we have one y and many x, so now it's in a plane. Multiple linear regression, it's in a plane. Those two terms, actually, it's in mathematics, okay? So you may search it from Google. What is the difference between a line and a plane, okay? Hope it's helpful. So let me repeat it again. Right now, OLS finds the best fitting line. Sorry, right now, OLS finds the best fitting plane or hyperplane through many dimensions instead of a 2D line. You obviously can't do this minimization by hand once you have several axes, right? That's what the computer, or in our case, does for us. So here it's also a hyperplane. Okay, this slide gives us the exact same meaning of each beta, all right? On slide definition, beta j equal delta y over delta xj by how much y changes if the jth x increases by 1 unit, holding all other x and the error term constant, okay? In plain words, means beta j isolates the pure effect of one variable, and we freezing everything else in place. Now, here the most marginal, now here the most magic part of multiple regression, the first bullet. The multiple linear regression model manages to hold the values of other explanatory variables fixed, even if in reality they are correlated with the explanatory variables under consideration. Remember what is explanatory variables? Means x, right? What does it mean? So in the real world, our X are often correlated with each other, like education and experience or spending and family income. We can't actually go out and hold experience fixed while changing education for real people. But mathematically, OLS manages to statistically separate these effects for us, even though the data itself is messy and correlated. That's the power of this technique, okay? This is what we called ceteris paribus interpretation. Latin for other things equal. It's the same idea economists always want. Isolate one cause, freeze the rest. Okay, isolate one cause, freeze the rest. But important warning in the last bullet, this one only works if unobserved factors in mu doesn't change when we change an x. Okay, if changing education somehow also shifts something hidden in mu, our ceteris paribus story breaks down. This assumption is so important that it gets its own name later. We'll spend the whole next section on exactly this condition. Okay? So here we have, it has still to be assumed that unobserved factors does not change if the explanatory variables are changed. Okay, so here we have unobserved factors, which is in mu, does not change if the explanatory variables are changed. Those are x, right? X, right? Okay, so here a concrete example. So ceteris paribus stops feeling abstract. Let's see this model. We have grade point average at college, which is your GPA in college, equal 1.29 plus 0.453 times high school grade point average, which is high school GPA, plus 0.0094 ACT, means achievement test score. Let's see. Beta 1, 0.453. This is our beta 1 hat. So we need to read beta 1 hat this way. Holding ACT fixed. One more point of high school GPA is associated with 0.453 more points of college GPA. Or think of it as comparing two real students. They have the same ACT score, but students A's high school GPA is 1 point higher than students B's. Our prediction is that A's college GPA will be 0.453 higher than B's, okay? Because we assume the same ACT. That's the ceteris paribus part in action with real students. Now, look at beta 2 hat, which is 0.0094 on ACT. This means that holding high school GPA fixed, one more ACT point only adds 0.0094 to college GPA. This is very tiny, very small, okay? So even 10 more ACT points only add about 0.094, less than a tenth of a point on GPA. Okay, it's here. So this one is about how to interpret beta 1 hat. And here is for beta 2 hat. Okay, here 10 points on ACT, which means we have 0.094, okay? Even 10 more ACT points only add about 0.094, less than a tenth of a point on GPA. So the idea is that once you control for high school GPA, the ACT score barely matters for predicting college performance. Because look at the parameter, the coefficients here, right? It's so small. High school GPA is doing almost all the work. This is a nice real illustration of why we control for multiple factors. We compare row effects without controls could easily mislead you about which variable actually matters. Okay, algebraic properties of OLS regression. I bet you saw this one on simple regression model, but let me repeat it again. This slide is about things that are always true for OLS, no matter what data you throw at it. This is purely algebra, no assumptions needed yet, okay? This is about the properties, means always true. Okay, we have our fitted value here, y I hat equal beta 0 hat plus beta 1 hat xi1 plus beta 2 hat xi2 plus all the way through to beta k hat xik. This is our fitted or predicted value because it has a hat. And then we have our residuals, right? Mu I hat, this is our residual, always equal the true y minus the fitted y. Now, three properties that automatically fall out of how OLS is built. Because remember, OLS is defined as minimizing summation of squared residuals, right? Minimizing summation of squared residuals, which is minimize summation of squared residuals. This is the idea of OLS. That minimization forces these three things to happen, okay? The first one, summation of mu I hat equals 0, which means residuals are always sum to 0. Okay, residuals are always sum to 0. The positive arrows and the negative arrows exactly cancel out on average. This is the first property. The second one, what is this? The summation of xij times mu I hat equals 0. It means covariance between deviations and regressors are 0. Deviation here means mu hat. Regressor means xij. Okay, the covariance between them are zeros, or in other words, each x is uncorrelated with the residuals in the sample, okay? Makes sense. If some x still predicted a pattern in the leftover errors, OLS would just adjust the coefficient to soak up that pattern instead of leaving it in mu. The third one, y bar equal beta 0 hat plus beta 1 hat x1 bar plus all the way through to beta k bar hat times xk bar. So here we have y bar, x1 bar, xk bar. These are the sample average, okay? Those are sample average of y and x. The same idea, right? The same idea as before. What does it mean? The sample averages of y and of the regressors lie on regression line. Or we can say it, the regression line always passes through the point of sample average. If you plug in the average of every x, you get exactly the average of y, okay? You plug the average of every x, you will get exactly the average y. Those three are properties, okay? None of this requires any assumption. It's guaranteed by construction, just like a balance scale that's always perfectly level by definition of how you build it. The real assumption, the one that let us say OLS is unbiased, will come next. This slide finally explains how OLS manages that holding order fixed trick, okay, the mechanics behind it. Take a two-step recipe for getting beta 1, the coefficients on x1, okay? Suppose the step 1, we regress x1 on all other x, okay, like x2, x3, all the way through to xk. Take the residual from this regression, okay? This one, we're gonna get a residual. And then step 2, we regress y on the residuals from step 1. So here, the slope you get is exactly the same beta 1 you would get from running the full multiple regression at once. So why does this procedure work? Think about what the step 1 residual actually are, right? The residuals from the first regression is the part of the explanatory variables that is uncorrelated with the other explanatory variables. What does it mean? It means that the residuals from step 1 actually are, it's the part of x1 that has nothing to do with the other x. We've already scrubbed out any overlap with x2, x3, etc. What's left is pure x1, cleaned of any correlation with the other explanatory variables. So when we regress y on this cleaned up version in step 2, the resulting slope can only reflect x1's Owen effect on y. There's no leftover contamination from the other x because we already removed it. This is called partially out. It's really the mathematical proof behind everything we've said about ceteris paribus. OLS literally partials out the other variables' influence before measuring X1's effect. You won't need to do this two-step by hand in practice because we have R programming, okay? So this is how R computes beta 1 directly. But you guys need to understand this is what makes the holding other variables fixed claim believable and not just a magic phrase, okay? So we're gonna have our lab. So in the lab section, you will see the results. You will see the estimation results from R programming. And you have to know the mechanics, okay, the techniques behind the R programming, why it provides you that estimates, okay? This is the logic, okay? We call it partially out. Okay, I'm gonna cover up to this slide about partially out. If you don't understand, please review this recording again and again, because for me, I first learned econometrics when I was in my bachelor, and then I did it when I studied master. And of course, I learned it again when I studied my PhD, and also I chose the how we call that one, elective course about econometrics, okay? And right now, I'm teaching you guys. So basically, I learned it again. Can you count for me? Bachelor, master, PhD, and also elective course in PhD. And right now, I'm teaching you guys. So at least I learned it 5 times. So please review it if you don't understand. And I'll see you guys this Thursday. Okay? Bye bye.